Okay, so here we go again. All right, so welcome back. I hope everybody had a good weekend. Starting with section 1.5 now. So equations of planes in space. And I'm going to start off with how to motivate the equation for a plane. There's natural connections to geometry that are involved in this motivation. So here it goes. If you know about a plane, if you know a point in the plane and a vector perpendicular to the plane. All right, now this is how we're going to define the plane in the first place. What plane are we talking about that we want to find the equation of? If you give me a point and a what we're going to call a normal vector, then there is a unique plane that goes through that point and is perpendicular to that normal vector. Okay. All right. So with that information given, how would we create an equation? Now keep in mind what an equation is. An equation is a test, right? I want to have some test where I can plug in a vector x, point x, and then either the equation works or it doesn't work. It's a yay or a nay on, when I supply a point in consideration. All right, so here's the idea. And keep in mind x naught is in the plane and in is perpendicular to the plane. Okay. If the point I'm testing, x, if it's in the plane, notice, given that x naught is definitely in the plane, x naught that's one of the defining characteristics of the plane, well then this difference vector would be parallel to the plane. Right? This is arguably the big move. If the point you're testing is in the plane, then this difference vector will be parallel to the plane. And of course, parallel to the plane is not hard to see. If it's parallel to the plane, then it's got to be perpendicular to that normal vector. Right? And what's nice about the rephrasing it as perpendicularity is we have this algebraic way to say perpendicular. Dot product equals 0. It's all algebra, and algebra is great for tests. So this is our answer. This is the equation for a plane, and you can write that a little bit differently. I like to distribute the dot and move things around a little bit and remember it as this. So there you go, the equation for a plane. Okay, now a lot of people like to expand that out, and if you think about it, your normal vector is going to have coordinates. Let's say the normal vector's coordinates are A, B, C. This point that we're testing, x, this is going to have coordinates. I'm going to call them x, y, z, point being that those are the variables. Those are, I don't know what they are. They could be anything, depends on what point we're testing. So x, y, z. And then if you look at the right side of the equation, again, n is given, but also x naught is given. So this whole thing here, all given, these are, defining features of the plane, and so you can just do that dot product, get some value, some number, let's call it d. Okay, so this is an alternative way to write the equation, and this has a lot of appeal because it's written in terms of coordinates, and people tend to like that very often. But do keep in mind there's certain advantages to not having expanded things out. Inside of what's written up here, you can see structure. You can see that there is a dot product. That's geometrically meaningful. And while it's not that hard to see here, it's not explicitly written in this form. But anyway, I find that in my experience, this is the one that I memorize and that I find the most useful. Okay. All right. Now notice, furthermore then, this means that these coefficients, when you're looking at the, coordinate equation for a plane, the usual ax, by, cz equals d, right? Those coefficients give you the normal vector. After all, that's where they came from. They were the coordinates of the normal vector. So, very cool fact to keep in mind. Sometimes you will find yourself looking at an equation like this and tremendous amount of free information staring you right in the face, namely, whatever these coefficients are, that tells you your normal vector. Okay. All right, so let's see an example of how to use these ideas. Suppose I have a plane that's given as containing these 3 points, A, B, and C. There we go, 3 points. And as long as they're not along a single line, any three non-collinear points would define a plane, right? So let's ask, how would I find the equation of that plane? Now, to find the equation, I need two things. I need a point in the plane. Well, I've got three of them. Right? We got all the points in the plane we could possibly have any use for. So that's not a problem. What is the question, the big trick then is to figure out, but what is this normal vector? How am I going to find a vector perpendicular so that I can write this down, or said differently, so that I can write this down? Where am I going to get this normal vector? This begins what I'm going to call the puzzle aspect of this question, and a lot of these exercises that you'll find about lines and planes and stuff have this puzzle aspect. There are certain geometric objects that I have or that I know, and other geometric objects that I need, and how do I get there from here, right? And all of these puzzles, you have to just keep in mind, well, I've got various tools, and what tools can I use to take what I have and turn it into what I want? And like I say, it's a puzzle is what it is. So in this case, here's what I'm going to do. I'm going to first observe that having points in the plane, I can subtract, which gives me a vector parallel to the plane. And then likewise with A and C, I can subtract C minus A, and I get another vector parallel to the plane. Yeah. Okay, now what does that buy me? Is that what I'm looking for? Well, not exactly. But let's keep in mind what we're trying to get to, right? What we're trying to get to is a normal vector. I need a vector perpendicular to the plane, and the blue vectors are not, but it got me a little closer, and in fact, we're now one step away, because if you have two vectors parallel, then their cross product, being perpendicular to both, must be perpendicular to the entire plane, and so I can use the cross product as my normal vector. What do you think? Everybody happy with that? Yeah.
Let's say, could we have also defined like C minus B as a vector? Or
Yeah, sure, for sure. Yeah, there's no requirement that you have to go in alphabetical order or anything. Yeah, so if you wanted to instead use A minus B and C minus B, totally fine. Just one thing you want to be careful of is don't use B minus A and A minus B, right? That's not going to work. You do need two independent directions. Yeah, totally. Yeah.
And then also, once you look for the cross product, where it says let X not be either A, B, or C, no matter what we do, we can choose any of the points?
Correct, right? And so you can use any one of these 3 points. And one point of view on how I know that you can do that is look back up here at the equation of the plane, right? Where this right-hand side, what we're going to do with X naught is we're going to compute n dot whatever that point is. But a point of view you can take on this equation is any point in the plane will have always the exact same values of n dot x. And so, use any point in the plane that you want. Yep. Good stuff. Okay. All right. Okay, moving along. So here's a really nice fact about planes. This is, this comes up sometimes. I'm going to say surprisingly often that this comes up. And so it's a good thing to not have to think through at the time. It's good to have already thought this through and have it locked and loaded. And if nothing else, to know that this is something to be on the lookout for. And here it is. If it should turn out that there's no y's in your equation for your plane, let's just say there's no y's in that equation, your plane is parallel to the y-axis. Now, this is, I think, a big win because this is super easy to be on the lookout for. Just, look for, there's no y's in this equation, right? Easy at a quick glance to see if it's true. And if it is, you get a strong piece of geometric information. Right, so nice trick to be on the lookout for. Let's see why it's true. If there's no y's, well, then another way to say that is that your y term is 0y instead of by. Okay, all right, what does that mean? Well, what that means is that, again, keep in mind, when you have an equation, you can look at those coefficients. Those tell you your normal vector, right? And I will observe that normal vector is perpendicular to the y-axis, whose direction is defined by E2, namely 0, 1, 0, right? Easy dot product. That dot product's clearly 0. So those vectors are clearly perpendicular. Well, wait a second. We have my plane. Whoops, sorry, I wanted to be in highlighter mode. My plane is perpendicular to the normal vector by construction. And the normal vector we just observed is perpendicular to this vector. And you kind of, connect the dots there. And what follows then is, let's see, this is perpendicular to that. That's perpendicular to the other. You can see from the geometry, it means that these are parallel. Everybody happy? So, neat fact, and I want y'all to, if you're looking to, for a little practice problem related to this, you can state and prove very, very similar results about if there's no x's or if there's no z's. And one thing you could do is make sure you're comfortable with this argument, then put it away and don't look at it. Take out a clean sheet of paper and try to state and prove similar results about x and z. Okay, good practice. Okay, here's another one. This is another sort of puzzle type question. We're going to be looking to parameterize a line. This is a line L there. And what I'm going to give you about this line is it contains this point A, 1, 2, 3, and it is parallel to both of these planes. Let's see, I'll use blue here. Parallel to that plane and that plane, which are, let's see, here and here. Okay, so the direction vector V there has to be parallel to both of these planes. All right, how do we parameterize this line? Again, keep in mind that's our goal, is to parameterize the line. Well, we know what the structure of a parameterization is. Parameterizations look like this. I already have the point that the line goes through, so all I need to do is figure out this V vector, and then we win. Okay, so how am I going to find this V vector? So here's the idea. The idea is, well, V being parallel to the line, V has to be parallel to the plane. The plane is perpendicular to the normal vector, and so therefore V must be perpendicular to that normal vector. Everybody with me? And then likewise, analogously, V must also be perpendicular to that normal vector. So, again, find myself in a circumstance where I need a vector V, and it needs to be perpendicular to these vectors that I can immediately conclude from those equations. Again, with that coefficient trick, right? So I've got two vectors. I want to find something perpendicular to both, and, of course, the cross product is going to do that for us. So you cross those normals, that gives you a vector parallel to the line, and that completes our parameterization here. Yes?
When we see the jump in logic, I'm making cross N1 and N2. So that it is perpendicular to both of them?
Yeah.
So why did you cross?
Yeah, so that's one of the neat facts about cross products. When you take a cross product of two vectors here, so I've got my two normal vectors here. N1 and N2, right? When I take their cross product, this cross product is perpendicular to both of the inputs. That's one of the basic properties of cross product, is that cross products are always perpendicular to both inputs. And so the result here that I get, being perpendicular to N1 and N2, has got to be parallel to the line. Does that make sense? Yeah, cool. All right, yes?
How do you know L is perpendicular to the So like the lines x plus y equals 3 and x minus y plus z equals 0.
Well, the line is parallel. It's given in the statement of the question. I want the line L to be parallel to both of these planes. Yeah, parallel, not perpendicular. Yeah. Mm-hmm.
I understand the second equation being equal to 0 means that you can employ like the ax by thing, but what about x plus y equals 3? Like what happened to the constant of 3?
Oh, yeah. So what I'm doing there, I'm citing this result here, that when you have an equation in this form, right, these coefficients give you your normal vector. And notice that D just doesn't matter.
So D doesn't have to be.
Yeah, so different values of D. So if here's a plane with a normal vector, right, a different value of D will move the plane, but it won't change the direction that the plane is going. So that the D is just a way of recognizing, well, which of these many planes are we talking about, right? But you don't need to know which of these planes we're talking about if they're all parallel. The normal vector only depends on the not D part of it. Yeah. Cool. All right. Okay, so now I used a couple of geometric arguments in these last two examples that I'm going to call transitivity arguments. They're sort of geometric transitivities of a sort. So, for example, I pointed out that, well, P is perpendicular to N, and N, by calculation, was perpendicular to the y-axis. And as a result, I conclude that P must be parallel to the y-axis. Right? So transitivity in the sense that I'm taking two sort of, I'm connecting two observations and looking at the sort of the whole that comes out of that. And then likewise here, I had that this vector is parallel to, for example, this plane. This plane is perpendicular to that normal vector, and therefore this vector by transitivity must be perpendicular to that normal vector, right? So again, I'm calling these transitivity arguments. The big warning I want to give you is always think it through carefully. Not all transitivity arguments that kind of on the page look like they ought to be true, not all of them are. Very often, just, symbolically, it'll look like it ought to be true, but it isn't true. So, for example, vector parallel to a plane parallel to another vector, doesn't it seem like parallel to parallel ought to give you parallel? It really feels like it. If you're just looking at the symbols, it really feels like it ought to be. But look at the picture here. Vector parallel to a plane, right? Same plane now, parallel to another vector. Does that mean that there needs to be any relationship between these vectors at all? Nope, not at all. But maybe they're parallel, maybe they're perpendicular, maybe they're neither. There's just nothing. We got no relationship between V and W. Right? This is what I like to call a transitivity landmine. Feels like it ought to be true, but it isn't. Okay, here's another example. We have here two planes that are perpendicular. P and Q are perpendicular. Q and R are perpendicular. I mean, you would think that perpendicular to something that's perpendicular to something else, doesn't it feel like perpendicular to perpendicular ought to give you like parallel or something? It really feels like it ought to be, but with planes, it just isn't. And again, you can see these two planes, P and R, they definitely don't have to be perpendicular. They also definitely don't have to be parallel. There's just no relationship you can conclude there. Right? So, here's my rule on this. You can make geometric arguments, and you don't have to sort of, go back to sort of a high school level of, geometric facts to, prove the general result you're citing. If you do something like this, where you argue that, I know N and it's perpendicular to the y-axis, therefore the plane is parallel to the y-axis, fine. No further elaboration necessary. You're basically employing a true fact of geometry, right? So my point is not about what you have to prove. My point is, watch out. You don't want to cite what seems like a true fact that is actually just nonsense. So you don't have to prove your geometric results, but you do have to be right. Does that make sense to everybody? Okay, let's talk about how to parameterize a plane. Now, this is a different kind of parameterization than we've seen before. We've talked about parametric lines. We've talked about parametric curves. After all, line is just an example of a curve. This, however, is not a curve. This is a fundamentally different thing. This is a two-dimensional thing. It's a surface, right? So we're not going to be able to parameterize it in the usual way. Because it is two-dimensional, we're going to need two parameters. And our parameters, instead of just using t, I'm going to need two of them. I'm going to use s and t as my parameters. Okay, so the way we're going to do it, again, I can't parameterize something until I know what thing we're talking about. So I'm going to assume we're given, let me use a different color here. Let me use dark blue here. So I'm going to assume that I'm given a point in the plane. And I'm going to assume that I am given a vector parallel to the plane and you know what? I made bad color choices. Let me start better color choices here. Suppose I'm given a point in the plane and a vector parallel to the plane and another vector parallel to the plane. This is better. Okay. How will I generate arbitrary points like x here in the plane? That could be anywhere else in the plane. And the big idea is this. Scalar multiples of v, because v is parallel to the plane, these scalar multiples also parallel to the plane. Scalar multiples of w, again, also parallel to the plane. So look at this. If I were to start at the point A, that purple point, if I were to then add this vector SV, which is just a multiple of V, and if I were to then add this vector TW, which is just a multiple of W, then, well, I start here, and then I move by SV, and then I move by TW, and sure enough, that'll get me to some point X here, also in the plane. And furthermore, S and T are free parameters, right? S and T could be anything, and so you can get anywhere in the plane you need to get. Just let S tell you how far you want to go sort of in that direction, and let T tell you how far you want to go in this direction, and you get anywhere you need to get to. And this will kind of trace out the entire plane. That makes sense to everybody? All right. So a quick example. I'm just going to plug directly into this formula, basically. And keep in mind what we need in order to do so. I need a point in the plane, and I need a vector parallel to the plane and another vector parallel to the plane. These are the givens that I need to have. So here's the puzzle. Suppose I have, 3 points in the plane. Kind of like that last example that we looked at, an early example that we looked at a little while ago. Okay, 3 points in the plane. How am I going to use this formula? Well, I need a point in the plane. Cool, I have 3 of them. Take your pick, doesn't matter. I like easy numbers, so I'm going to pick A, but whatever, it doesn't make any difference. Any point in the plane will do. Okay. What else do I need? I need a couple of vectors parallel to the plane. Well, we saw this trick previously, and I can just pairwise subtract B minus A, C minus A, for example. There's other options, of course. And now we're in business, and so I'm going to use A as my point in the plane, and I've got these 2 difference vectors to be my parallel vectors, and plug them in with my parameters per the formula above, and we have ourselves a parameterization for that plane. What do you think? Everybody's good. All right. Okay. So, there's a category of questions involving lines and planes and points and stuff, namely, how do I find various distances? So, distance from a point to a line, distance from a point to a plane, distance from a line to a plane, all these kinds of things. I'm going to show you some examples of such questions and how to solve them. The big idea here is notice the trick that makes it work. These are tricks that I'm showing you for free, right? You don't have to have thought of these tricks on your own. These you get to steal and use the same tricks that I have been using that I stole from my predecessors who stole them from someone else, right? So we're passing along the tricks here. Okay, so suppose we have a point and a line. How am I going to compute this distance from the point to the line? Notice that it needs to be the perpendicular distance. Of course, there's lots of paths that you could follow to get from the point to the line. When we say distance, we mean the shortest possible. Okay. All right, so that's going to be, again, a perpendicular. So step 1, pick any point that you want on the line. Doesn't matter. Any point at all. Pairwise subtract here, like this. And that gives us, that's not immediately useful. That's just some random vector, right? As it stands, not useful. But if I were to look at the projection down to the line, just project, we've got a direction vector v there. Right? If I look at that projection, this useless orange vector, if I subtract off its projection, that difference is this vector here, whose magnitude gives me the distance that I wanted. So, lovely little trick. Vector minus its projection. Set up as we have it here. We'll tell you that distance. Did everybody see what happened? Yes.
Could you also use a Pythagorean theorem or no?
Well, the problem is you don't know what to plug into that, right? So, let's just think it through, right? So I know this point is given, and let's see this. Let's suppose further that this point is given, because it might as well be, right? How do I know where that is? Right? I don't know where that corner is, and so I don't know how to compute that distance in the first place. So, it's just, hypothetically we could, we just don't have the information to be able to plug into it. Does that make sense?
Yeah.
Yeah, cool. All right. Okay, so useful trick. I'm going to show you 2 different methods for answering this question. Keep in mind, our goal is not to get an answer, our goal is to learn tricks and tools and ideas, right? So this is one idea that is very often useful. Here's a different one that in other circumstances might be useful. Again, point given, line given. Line is given by way of there being some point on the line and some vector parallel to the line. How am I going to find that distance? The big broad stroke on this solution I'm going to show you is it's a very tricky approach. I'm going to compute what I want by starting off computing something totally different. I'm going to compute this area that I am actually not interested in. Believe it or not, computing something you don't want can help you compute something that you do want. In particular, we're going to compute it 2 different ways. See you down there. I'll go through the details in a minute, but notice I'm computing that yellow area 2 different ways. Again, details to come. And by computing it 2 different ways, I find myself with knowing that these 2 things are equal. So if the thing that you want, this distance, if that thing that you want is involved in one of the computations, then computing this thing that we did not want, again, I don't care about the area, nobody asked me about the area, but by computing that area 2 different ways, I get an equation that involves the thing that I do want. Right, so this is a very indirect approach to finding distance. But if, in the absence of a more immediate way to do it, this is a foot in the door, right? So another way to say this, if you want to compute something, you don't have to go straight at it. If you want to compute something, just involve it in the computation of anything. And then compute that anything by some other method, and boom, you've got an equation that involves what you want. Yes? How the what now? Oh, yeah, I'm going to get to that. I haven't done that yet. Yeah, absolutely. Okay, let's go ahead and do that now. But before, does anybody have any questions about the big picture strategy? Everybody sees the big picture? Okay. All right, so yeah, how do we know this, you ask? And so let's see here. Here is our parallelogram again. And an old fact about parallelograms, you may recall from high school geometry, is that the area is equal to height times the base. And the height is the distance that I want. And the base, and again, just looking at this particular scenario, the base there is exactly the magnitude of that vector being this projection. So height times base, turn your head slightly to the right to, make it look better, and there you go. That computes that area. Does that make sense? Yeah. So what I'm using here is an old fact from high school geometry. If you have a parallelogram, now let's see here. I'm going to try to draw a decent parallelogram. So parallelogram, right? If you know the height and if you know the base, right, then the area in here is height times base. Does that one sound okay? So that's all I'm doing here. It's just that here I've got a height times a base. It's just that everything's kind of turned to the side a little bit, but I can view this as being, if you will, the horizontal, right? And then that's the height and that's the base. Is that cool? Okay, great. Yes?
So, here, I think the height managed to also be the diagonal.
That's a coincidence. No, that's a great observation. It's a coincidence based on the fact that this base is literally a projection, right? And that's not generally here that's certainly not the case. Here if you look at this edge and if you were to drop a perpendicular to find the projection, that projection is not the same as this because it just wasn't set up that way. So this is a special parallelogram. It's not a generic parallelogram. Is that cool? Yeah. All right. Okay, so now we're not done. What we have done here so far is we have shown that the thing that we want is involved in a calculation of something that I also don't know, namely area. So I've related what I don't know and want to something that I don't know and don't want. Okay, but again, there's a next step. The next step is to relate this thing, this thing that I don't know and don't want, relate it to something else. We're going to find another way now to compute that area, and this is going to be to cite an old fact from the, last section or 2 sections back, I forget, fact about parallelograms. If you know 2 edge vectors, the cross product of the 2 edge vectors will have magnitude equal to the area. Everybody remember that one from 1 point whatever? Okay. All right, so again, the whole point is I didn't really care about the area in the first place. What I really wanted was this distance, and that distance happened to be involved in one of these 2 calculations of area that I still don't care about. Point of which is that now distance is involved in an equation where I can compute. And so just, solve for D and you're in business. Okay. All right, next question. Distance between parallel planes. Again, we have this problem if we want specifically to refer to perpendicular distance. It needs to be perpendicular distance. Otherwise, there's lots of different distances that one could argue from one plane to the other plane. You know, when I say how far is it from here to somewhere else, I mean, of course, what is the shortest possible path? Okay, so perpendicular distance. And the neat observation is that if you take any displacement vector, just the difference between any 2 points, you know, from one plane to the other plane, any difference vector at all, and you look at its component in the normal direction, well, that component in the normal direction is the distance I'm looking for. That one is kind of an immediate win. One step argument. Is everybody happy with it? Okay. All right. Okay, the next one, very tricky. Suppose I have 2 skew lines. Reminder what skew means. Skew means worst case scenario. It means they don't intersect, they're not parallel, they don't have anything in common. So no good news, just 2, in some sense, kind of random lines with nothing in common. No points, no direction shared. Okay, how do we find the distance? And again, distance means shortest possible, so I don't mean, let me avoid the perspective problems. I don't mean that, right? I mean imagine perpendicular, it would be something like, something like that. So perpendicular there and perpendicular there. So I want the perpendicular distance. Everybody good? The very, very clever observation that I did not think of on my own, somebody showed me, now I'm showing you, is I'm going to cite a result that I will prove in a minute, but I claim that when you have 2 skew lines, those 2 skew lines lie inside of parallel planes. Now I'm going to prove that in just a minute and show you how to find them in just a minute. But let me show you why we care about this. Once you know that they're in parallel planes, then check it out. The distance that I want, this shortest possible distance, perpendicular distance between the 2 lines, is also the distance between those 2 planes. That make sense? So what an odd trick, but that totally does it. And how do we find the distance between 2 parallel planes? Oh, well, we've got a pre-existing formula for that, so that's no problem. So what remains, though, is how do I establish that there truly are parallel planes containing these 2 skew lines? That's this is the tricky part. And here's the idea. What I really need in order to do this is to find this direction vector. This normal vector in. I need to find the vector perpendicular to both of these planes, so I know which direction they're pointing. And again, there's kind of a transitivity here. I know that this vector, this V1 vector that I have, is parallel to L1, which means it's parallel to the plane, which means it's perpendicular to the normal vector I'm trying to find. And this direction vector V2 here, parallel to L2, that means it's parallel to this plane, which means it's perpendicular also to the exact same normal vector that I'm trying to find. And so this normal vector I'm trying to find, I'm going to find it by then just crossing the 2 things that I know it has to be perpendicular to. Is that cool? Everybody's good? Yeah.
So the normal vector, the distance?
One more time, I'm sorry.
Is the normal vector the distance between them?
The normal vector is just a vector. What this normal vector does is it allows me to identify these parallel planes. And once I know the parallel planes, then I've got to go back up to here and use this technique that I have up here to find the distance between parallel planes, namely compute with that formula. Yeah, pick any 2 points and subtract and find the component in the in direction. Yep. Yes.
Sorry, can you explain one more time how you use the, can you go down?
Yep.
How you use the normal vector to find the parallel planes?
Well, so the normal vector is just kind of what I need, right? So I already have these two lines, and I've got points on the lines, and I've got vectors parallel to the lines. I know everything I need to know about the lines. What I need in order to be able to find these planes is I just need to know what is this normal vector, because that's what defines a plane: a normal vector and points. So I'm good on the points. I've got, for example, that point right there, or some points anyway on the line, and I've got this point over here or whatever. I've got points on the line. I just need the normal vector so that I can say, well, I've got a point in the plane, I've got a vector perpendicular to the plane, and then we just use our first formula from today. Does that make sense? Yeah. Okay. Yes.
What's the difference between a component of a vector along another vector and the projection of that vector along?
Right. So the difference between a component and a projection is a component is a scalar. It's kind of it's like a distance, right? Yeah, and a projection is a vector.
So the magnitude of the projection is the component.
Very close, and I know what you'd say. So mostly yes. There is a little asterisk. Magnitudes are intrinsically positive. Components don't have to be positive, but the absolute value of the component is equal to the magnitude of the projection. But the component could be negative. Like if your direction vector is like that and your other vector is going back the other way, the component would be negative. Yeah. Okay, so that does it for 1.5. Where am I drawing the line? We've got 10 minutes left. But I do want to get started into 1.7. Notice that we've already done 1.6, so moving along to 1.7. We're going to talk about new coordinate systems. Real quick, I want to start by talking about rectangular coordinates. This is what most people think of as being just, the coordinates in the plane. And y'all know the deal with rectangular coordinates. You see why they call it rectangular coordinates. The picture makes a rectangle. I think it's pretty believable. And a couple of neat things to say about them, though. First of all, they're unique. And this is an underappreciated observation. But if you have a point in the plane, there is exactly one x-coordinate. And there is exactly one y-coordinate. So you can talk about the coordinates of a point in R2, in rectangular coordinates of a point in R2. So this is what I mean by saying rectangular coordinates are unique. Bad news, all of the other coordinate systems we're going to talk about in this section don't have this property. So this is a luxury of rectangular coordinates that we're going to have to get used to doing without. Okay, and examples to follow. Okay, next thing, algebraic convenience. Of course, we have this really handy relationship about how to relate the coordinates of a point with the coefficients in the linear combination of standard basis vector that gives you that point. Right? This is arguably this is the definition of coordinates in some senses. What multiples of E1 and E2 get you to that point? Okay. All right. And now here's a kind of a broader statement. If you were doing algebra of vectors, for example, adding scalar multiples, namely taking a linear combination of vectors, you could just take the same linear combination of the coordinates. Super handy. Gotta love it. This, again, is a luxury of rectangular coordinates. The analog of this statement also not true in like polar coordinates, spherical coordinates. It just doesn't work. So that is unfortunate. And again, we're just going to have to deal with not having this feature. All right. Okay. Jumping in, polar coordinates. Some of y'all may have seen it before. If you have, great. If you haven't, no worries. I like to think of polar coordinates in relation to the function that converts from polar to rectangular. And the idea is that if you give me an r and a theta, these are called the polar coordinates of the point we're about to look at in the xy plane. If you give me an r and a theta, and if you understand the theta as defining a direction as follows. go counterclockwise from the positive part of the x-axis. That defines a direction. And then use r, the other polar coordinate, as an indication of what I'm going to loosely call how far to go in that direction. Right? Then notice that gives you a point in the xy plane. So set up in this way, r and theta are what we call the polar coordinates of that point in the xy plane. How are we doing? Is everybody okay? Now, let me clean up my sloppiness. I say how far. R tells you how far to go. How far implies a distance. Distances are positive. That's a problem because R does not have to be positive. It's perfectly acceptable for R to be a negative number. So look, this is a problem of language mostly. That's why I had to put the quotes here on how far. We can totally handle the issue if you have a negative value of R. Well, no problem. If this is what you do for positive, wouldn't it make sense that you just go the other way if R is negative? And that's all we do. If R is negative, then you just go backwards by that same amount, whatever the absolute value is. Okay. All right. Okay, so that's polar coordinates. Here's an exercise for y'all to think through. A nice little refresher trig problem. You can look at that triangle right there where you see r and theta, and of course you can see x and y on that triangle as well. And with that in mind, that triangle in mind, x is r cosine theta, right? And y is r sine theta. So I hope that's clear. Think through the details. Make sure that you're comfortable with that. And so cool facts relating these coordinate systems. And now we're going to go on and see some of the weird things about polar coordinates. So let's talk first about the failure of uniqueness. So let's take this point right here. There's a point in the xy plane, and I'm going to say that it's some angle off of the positive part of the x-axis. I'm going to presume that this distance here is 5, just so we can, just get the ball rolling here. So there's a point. Whatever the angle is, let r equals 5. You can think of this as the polar coordinates for that point, because the angle theta, that angle theta defines that direction, and then you go a distance 5 in that direction. That gets you the point. That's a distance 5 from the origin, and boom. Fine, no problem. Why are we worried about this? Well, here's the thing. What if you were to add 2 pi to the angle? Add 2 pi to theta. So I'm going to add 2 pi to the angle, which of course just takes you a full turn around. And notice that means you're going in the same direction. So whatever that theta is, theta plus 2 pi, as far as the xy axis, xy plane is concerned, theta plus 2 pi puts you in exactly the same direction. And so this right here, just as good. 5 comma theta plus 2 pi, same point in the xy plane. So this is an example of the failure of uniqueness, right? This purple point has 2 different sets of polar coordinates that we've found so far. You can think of these as being polar coordinates for it. You can think of those as being polar coordinates for it. They're both equally good. All right, now there's another thing you could do, and that is don't add a full 2 pi, add just pi. If you add just pi to your angle, that gets you going exactly the wrong direction. But keep in mind then, I know that, then in this direction, I need to go backwards. I need to go negative of the amount 5. And so let's make r then equal to negative 5. And again, that gets you to that same point. So, negative 5, comma, theta plus pi, also perfectly acceptable polar coordinates for that point. Everybody with me? All right. Okay. Okay, and I see now that I'm out of time. Okay, so we'll draw the line right here. We will pick up here on Wednesday. And I hope y'all had a good weekend. Welcome back, and see you on Wednesday.